The dominant theory among the majority of scientists is that the current explanations for where the universe came from remain the leading interpretation of its early development. Based on this hypothesis, the development of stars and planets ultimately led to the emergence of life, including humans. Despite its bizarre title, the Big Bang provides a comprehensive view of what might have occurred at the universe's dawn. In the beginning, the entire universe was concentrated in an extremely small space, considerably smaller than the head of a pin, packed with particles. From this densely packed state, an enormous release of matter and energy, known as the Big Bang, occurred. This cataclysmic event, which took place billions of years ago, set in motion the extensive history of the universe. As scientific understanding advances, however, discrepancies have started to arise, casting doubt on the assumptions of this theory. When NASA launched the James Webb Space Telescope, JWST, the biggest and best space observatory ever built, experts expected that its observations would verify the Big Bang theory. However, within just 1 year of its launch, the telescope amazed scientists with its extraordinary ability to peer into the universe's distant past. The JWST's innovative capabilities have uncovered galaxies that date back so far that they challenge the current understanding of the universe's origins. This discovery has sparked a wide debate about the possibility of pre-Big Bang matter. A major breakthrough came when cosmologist Rohan Natu, analyzing data from the telescope, discovered a galaxy that existed shortly after the Big Bang, marking it as the most distant galaxy presently observed. This discovery sent shockwaves through the scientific community, highlighting the remarkable capabilities of the James Webb Space Telescope. The immense potential of the JWST to alter our perception of the cosmos is just beginning to take shape. With significant revelations about the universe's earliest stages, this period, loosely connected to prior cosmic events, holds the key to understanding the formation of the first stars and galaxies. The findings from the JWST have contradicted existing theories, revealing galaxies with features that defy previous expectations. This surge in the discovery of early galaxies has ignited a flurry of scientific research, pushing professionals to reconcile these new revelations with established theories. As scientists delve deeper into these findings, they must confront fundamental inquiries regarding the essence of the universe and the forces that guided its evolution. In addition to its scientific advantages, the JWST is strategically positioned 1.5 million kilometers away from Earth, protected from interference while remaining at nearly absolute zero due to the size of its sun shield. This location allows the telescope to capture unimpeded observations of the universe without the distortion of Earth's atmosphere. Equipped with a massive primary mirror and sophisticated instruments, the JWST was specifically designed to uncover details about the early universe that were previously out of reach. This early cosmic era, referred to as the Great Dawn, began approximately 200 to 300 million years after the Big Bang, when the first galaxies and stars began to form. The mechanisms behind this process remain a key area of research, with various theories exploring the roles of dark matter, dark energy, and the interactions between dust and gas in star formation. The JWST's ability to observe galaxies from this critical period provides a one-of-a-kind opportunity for cosmologists to test their existing models of a universe. By studying these ancient galaxies, scientists can either validate current theories or discover gaps in their understanding that may lead to revolutionary revelations. At first, the JWST was anticipated to detect only a few faint, small galaxies in their earliest stages. However, its observations far exceeded expectations. The telescope's first images of the distant universe revealed an astonishing number of galaxies with varying ages, sizes, and luminosities, much higher than previously anticipated. This sudden influx of early galaxy discoveries has sparked intense activity in astronomy. Scientists are now racing to redefine the record for the earliest massive systems known. New discoveries are being made every day, leaving even seasoned researchers in awe. Following the JWST's findings, both experts and the general public have been eager to learn more about the traits of these highly advanced early galaxies. Some theorists have suggested that potential errors in how the telescope interprets observations on a large scale might account for some of these remarkable findings. However, the general consensus remains that these revelations represent a paradigm shift in our understanding of the origins of the universe. They offer an exciting glimpse into how much more we have yet to learn. The recent discoveries of ancient galaxies, made possible by the JWST, have raised significant questions about the nature of the universe. While some researchers are exploring ways to integrate these discoveries into existing theories, Others suggest that these findings point to a far more complex and mysterious universe than previously anticipated. The critical question that remains is, how did the universe we know today emerge from the chaotic turmoil of its early stages? The JWST's early findings could fundamentally alter our perception of the Big Bang and offer fresh perspectives, not only on distant galaxies and ancient cosmic structures but also on the very makeup of our own Milky Way galaxy. As Mark McFadden, senior scientist for research at the European Space Agency, aptly put it, "You build these machines not to confirm theories but to break them. You simply have no clue how it will break." The JWST project was established in 1985 at the Space Telescope Science Institute, STSCI, long before the launch of the Hubble Space Telescope. At that time, G. Weir, then head of STSCI, was tasked with imagining what could come after Hubble. Despite early skepticism, Weir and a small group began laying the groundwork for what would ultimately become the James Webb Space Telescope. Unlike Hubble, which primarily observes visible light, the JWST was designed to observe in the infrared spectrum, allowing it to see deeper into the universe. This infrared capability is crucial for studying the early cosmos, as it enables astronomers to detect light from some of the oldest galaxies ever formed. Galaxies far away, whose light has been stretched into the infrared due to the universe's expansion, render them invisible to telescopes such as the Hubble. Its large, cold, star-like mirror, the JWST, has evolved into a necessary instrument for unlocking the mysteries of the great dawn of the universe. The need for such a telescope became apparent in 1995 when the Hubble's observation of the deep field revealed a vast number of galaxies in a region previously thought to be empty territory in the sky. This discovery demonstrated the early universe's riches and highlighted the necessity for a more powerful and capable telescope to observe even further into the cosmos. After years of development and an investment of around $1 billion, the JWST was launched on December 25, 2021. By July 2022, it was ready to begin its critical year of scientific observations. Programs like the ERS, Early Release Science, and the General Program of Observations were specifically designed to search for early galaxies. In contrast to modest expectations, the results far exceeded projections. The JWST's observations have already begun to challenge previous early-era models of the universe, uncovering galaxies that defy conventional cosmological assumptions. These remarkable discoveries emphasize the significance of pushing the boundaries of scientific exploration and highlight the remarkable capabilities of cutting-edge technology like the James Webb Space Telescope. As scientists continue to analyze the data from the JWST, new insights may emerge that challenge us further and expand our understanding of the universe. When the initial data from the JWST began to arrive, cosmologists eagerly awaited the results. Many scientists had spent years preparing their systems for data analysis. For the time being, as opposed to following the conventional peer review system, which can take weeks or months, researchers chose to share their results on preprint servers such as AR14, where papers can be publicly accessed before undergoing peer review. This approach allowed for rapid feedback and discussions through online platforms like Twitter, where established scientists could quickly engage in dialogue about the findings. Rohan Natu called this new method science by means of a press release. The subsequent surge in conversation was lively and unprecedented, but there were concerns about its potential drawbacks. Swift dissemination of results caused Klaus Pontoppidan, a JWST project scientist at STSCI, to caution that while rapid sharing of findings allowed for communication and discussion, it also risked overwhelming the scientific process. The accelerated spread of discoveries, particularly in such a groundbreaking mission, introduced challenges to traditional scientific workflows. Despite the rapid pace of data release, the general consensus among most experts is that the prevailing theory explaining how the universe got its start remains essential for comprehending the early stages of the cosmos. Star formation, as this theory suggests, eventually led to the formation of planets and, ultimately, life, including human life, as a crucial component of the universe's development. Despite its odd name, the Big Bang Theory provides a clear explanation of the universe's beginnings. In its earliest stages, the universe existed as an extraordinarily dense point, far smaller than the tip of a pin, filled with tightly packed particles. From this incredibly compact state, a colossal release of matter and energy, the Big Bang, unleashed the forces that would shape the universe. This massive event, billions of years ago, set the stage for the universe's evolutionary journey. As scientific understanding develops, however, inconsistencies have surfaced, challenging long-held assumptions. When NASA launched the James Webb Space Telescope, JWST, considered the most advanced and largest space observatory ever built, there was an expectation that its observations would provide strong evidence for the Big Bang theory. Yet, within its first year of operation, the telescope astonished researchers with its unprecedented capacity to look back in time. The JWST's remarkable capabilities have uncovered galaxies from an era so ancient that scientists are now forced to reconsider what we know about the universe's formation. This revelation has triggered discussions about the possibility of pre-Big Bang matter. A major breakthrough was achieved when cosmologist Rohan Natu, analyzing data from the telescope, discovered a galaxy that formed shortly after the Big Bang, making it the most distant galaxy presently observed. This discovery sent shockwaves through the scientific community, underscoring the JWST's extraordinary power to deepen our understanding of the cosmos. The vast potential of the JWST to reshape our view of the universe is just beginning to unfold, offering significant insights into the very beginning of cosmic history. This period, which vaguely aligns with previous cosmic theories, is essential for comprehending the origins of the first stars and galaxies. The JWST's discoveries have defied established theories, revealing galaxies with characteristics that surpass prior expectations. This flood of early galaxies has prompted a wave of scientific investigation, pushing researchers to reconcile these new findings with existing theories. As scientists continue analyzing the data, they are confronted with profound questions regarding the fundamental nature of the universe and the forces that paved the way for its evolution. As the JWST continues its observations, scientists are grappling with the implications of these groundbreaking discoveries. The telescope has detected galaxies forming much earlier than previously thought possible, raising fundamental questions about the timeline of cosmic evolution. These findings suggest that the early universe may have been more dynamic and complex than our current models predict. One of the most astonishing revelations is the discovery of massive, mature galaxies that existed just a few 100 million years after the Big Bang. According to traditional cosmology, galaxies of this size and structure should not have had enough time to form. This has led researchers to reconsider how quickly star formation and galaxy assembly could occur in the early universe. In addition to these early galaxies, the JWST has also provided unprecedented insights into the atmospheres of exoplanets. Using its powerful infrared instruments, the telescope has detected key molecules, including carbon dioxide, methane, and water vapor, in distant planetary atmospheres. These findings have significant implications for the search for extraterrestrial life, as they help scientists identify planets that may be capable of supporting life. The telescope's ability to analyze exoplanet atmospheres with such precision marks a major leap forward in astrobiology. By studying the light passing through these distant atmospheres, researchers can determine their chemical composition and even assess their potential habitability. This has opened new doors in the search for biosignatures, chemical indicators of life, on planets beyond our solar system. Beyond exoplanets and early galaxies, the JWST is also shedding light on the life cycle of stars. Its observations of nebulae and star-forming regions have provided breathtakingly detailed images of stellar nurseries, where new stars are born. By studying these regions, scientists are gaining deeper insights into the processes that govern star formation, planetary system development, and the distribution of elements essential for life. Despite its remarkable achievements, the JWST's discoveries have also sparked controversy. Some of its findings challenge long-standing assumptions in cosmology, leading to debates within the scientific community. For example, the detection of ancient, large galaxies has raised questions about whether our current understanding of dark matter and dark energy is complete. These invisible forces are believed to shape the structure of the universe, yet the JWST's observations suggest that early galaxies may have formed in ways that existing models struggle to explain. As researchers continue to analyze the vast amounts of data being collected by the JWST, it is becoming increasingly clear that our understanding of the cosmos is evolving. The telescope is not only confirming existing theories but also revealing new mysteries that require fresh perspectives and innovative models. Looking ahead, future missions may build upon the JWST's success, pushing the boundaries of exploration even further. Proposals for next-generation telescopes, such as the Habitable Worlds Observatory and the Origin Space Telescope, aim to expand our ability to study exoplanets, galaxies, and the fundamental forces that shape the universe. These missions, inspired by the JWST's groundbreaking discoveries, will help scientists refine their understanding of the cosmos and search for answers to some of the deepest questions about our origins and place in the universe. As humanity stands on the brink of a new era in space exploration, the JWST serves as a testament to the power of scientific curiosity and technological innovation. Its ability to peer into the distant past and unveil cosmic secrets is transforming our view of the universe. With each new observation, the telescope is rewriting the story of our cosmic origins, challenging us to think beyond our current understanding and inspiring future generations to continue the quest for knowledge. Impressive scientific contributions of the JWST. The JWST's strategic positioning, 1.5 million kilometers from Earth, keeps it protected from interference and nearly cooled to absolute zero by its sunshield. The size of a tennis court, this positioning provides a unique advantage, enabling the telescope to record fine-detail observations of the universe without being affected by Earth's atmosphere. Equipped with a large front-view mirror and sophisticated instruments, the JWST was specifically designed to capture unprecedented details about the early universe, details that were previously out of reach. To detect this early period in cosmic history, known as the Great Dawn, scientists focus on a time roughly 200 to 300 million years after the Big Bang, when the first stars and galaxies began to form. The mechanisms driving this process remain the subject of intense research, with various hypotheses suggesting the role of dark energy and interactions between gas and dust in star formation. The JWST's ability to observe galaxies from this important era provides cosmologists with a unique opportunity to test their models of the universe's early stages. By studying these ancient galaxies, scientists have the opportunity to either confirm existing theories or uncover new gaps in our knowledge, potentially leading to major discoveries. At the beginning of the JWST's observations, it was expected to detect only a few faint, small galaxies. However, the results far exceeded these predictions. The telescope's first images showed a surprising number of galaxies, varying in age, size, and luminosity, far surpassing what was anticipated. The sudden influx of early galaxies has sparked a race among astronomers to analyze the data for the earliest known massive galaxies. New discoveries are being made regularly, leaving even the most experienced scientists in awe. Both experts and the public have become increasingly focused on the advanced features of these early galaxies. While some researchers suggest that the telescope's large-scale observations might explain these surprising results, the prevailing view is that these discoveries represent a significant shift in our understanding of the early universe. They provide an exciting glimpse into the potential for future breakthroughs. The recent discoveries made by the JWST have raised significant questions about the nature of the universe, challenging long-standing assumptions in cosmological theory. While some experts are working to integrate these findings into existing models, others suggest that they may be the first indications of a universe far more complex and mysterious than previously envisioned. The crucial question remains: how did the universe as we know it emerge from the chaotic and turbulent conditions of its early stages? The JWST's early discoveries may significantly reshape our understanding of the Big Bang, offering new perspectives not only on distant galaxies and ancient cosmic structures but also on the very nature of our own Milky Way galaxy. As Mark McFadden, a senior scientist at the European Space Agency, said, "You don't make these machines to confirm theories, but to break them. You simply do not know how it will fail." The JWST's origins and technological advancements. The JWST's beginnings can be traced back to 1985, when the Space Telescope Science Institute, STSCI, began planning for a successor to the Hubble Space Telescope. At the time, Garth Weir, the head of STSCI, was tasked with imagining what would come after Hubble. Despite initial doubts, Weir and a small team laid the groundwork for what would eventually become the James Webb Space Telescope. Unlike Hubble, which primarily observes in visible light, the JWST was specifically designed to observe in the infrared spectrum. This allows it to peer deeper into the universe, as the light from distant galaxies has been stretched into the infrared due to the expansion of the universe, making them inaccessible to telescopes like Hubble. Equipped with a large, cold, star-like mirror, the JWST has become an invaluable tool for unraveling the mysteries of the Great Dawn. The need for such a telescope became evident in 1995, when Hubble's deep field observation revealed an abundance of galaxies in a seemingly empty patch of sky. This discovery highlighted the richness of the early universe and underscored the necessity for a more powerful telescope capable of gaining deeper insights. After years of development and an investment of around $10 billion, the JWST was successfully launched on December 25, 2021. By July 2022, it was ready to begin its most critical year of scientific observations. Programs like the Early Release Science, ERS, and the General Observing Program were specifically designed to search for early galaxies. Despite initial modest expectations, the JWST's observations have already begun to challenge existing models of the early universe, unveiling galaxies that defy conventional cosmological assumptions. These groundbreaking discoveries emphasize the importance of pushing the boundaries of scientific exploration and demonstrate the extraordinary capabilities of modern technology. As researchers continue analyzing the JWST's data, new insights may emerge, expanding and refining our understanding of the universe. When the first data arrived, astronomers eagerly awaited the results, knowing that many had spent years preparing their data analysis systems for this moment. The discoveries made by the JWST could very well redefine our comprehension of the cosmos.